All right, ladies and gentlemen, good morning to you guys. Welcome back after a nice Thanksgiving break. Hopefully, you guys did work on antiderivatives, but if you didn't, well, it'll be a learning lesson for you. Good luck. I've given you what's called fair warning. Anyway, let's take a look here. What are we doing here? Let's go to my website. I have to go to my website. Sorry, that's not you guys. That was trig. They're working with vectors. So if you guys had a good trig course, hopefully you talked about some vectors. That's what I'm doing. So this isn't trig. You're doing calculus. Let's find that out. Hey, that's not where you're going. Where are you, calculus? All right, numerical approximation to area under a curve. Now, this is a big part of calculus, believe it or not, this idea. And this is a very, very important process that you're going to see through calculus 1, 2, and even 3. This process we'll talk about. This is trying to find the area under a curve. Here's the curve, obviously, I hope. And it's going to be between the lines x is A and x is what? B. Okay, here's a process. The question's going to be, what is A here? This is A for area. So you guys know we got area here, A. And it's a numerical approximation. So it's not going to be exact. It's going to be approximate. Okay? And I want you guys to note something important, that your function y is actually greater than or equal to 0. It's actually strictly positive in this picture for all x in the interval from A to B here. So you're going to have an interval, always an interval between these two values, A and B. And there's the area. Now, here's what we're going to have to do. Here's the first step in your process always. You're going to partition your interval, AB, into what we call n subintervals of equal length, delta x. Okay? So you might say, what are they talking about here? Well, in the picture, here's the interval from A to B. There should be an x naught here. I don't know what happened. Hope it didn't fall off. Okay? So they're talking about partitioning your interval AB. And they want you to partition that AB into what we call n subintervals of equal length. And they call that length delta x. Now, in order to do that, you need the length of the whole interval. And then you divide by the number of partitions. That is called your delta x. All right, so you get the whole length of the interval, which is B minus A, and divide by the number of partitions. And that's kind of the picture they're talking about here. You partition these intervals into n subintervals here. And then that's why you're going to see these subscripts x1, x2, so on, all the way up to xi minus 1, xn minus 1, xn. So you're going to see these partitions here. And the distance between these partitions down here is all equal length delta x. And this is a very important formula here that I want you guys to actually really pay attention to. Okay, you guys are going to be using that part, that delta x definition. If I can draw a rectangle. And this is your n subintervals. Okay. All right, so this is a classic demonstration, ladies and gentlemen. And so here's what's going to happen now, right? So this is an important piece. Let's go back maybe to talk about this piece right here. This is your ith, what we call the ith subinterval right here. Okay? So let's call it the ith subinterval. ITH subinterval, and that's really this interval right in here. We have xi minus 1 xi. So you're looking at this subinterval here. And associated with that subinterval, you're going to have what we call a rectangle here now. And I try to draw a point here. So here's really what you're looking at, okay? This is really the meat and potatoes of what's happening here. So you look at that ith subinterval, where the point is xi minus 1 comma xi, and you find that this is a rectangle, and we call this rectangle actually AI. So you say, okay, here's the ith rectangle. And you have more rectangles here. Okay, this is like the first rectangle. Starts with x naught to maybe x1, if we can draw this right. And then we have another rectangle right in here. So you're going to have n rectangles, by the way. So that's kind of the essence of this process here. Here's your first rectangle with your first area. Here's your second rectangle with the second area here. Okay, so this is like called A1, and this will be A2. And so you're going to end up here at the very end with an nth rectangle. And all of these here have a delta x, I should say width. A constant width of delta x here. So we're setting the table with a calculus sort of process that you're going to see, you know, over and over again in every sort of calculus setting. Okay, we're going to try to approximate the area under the curve using rectangles. Now, do you guys know, how do you find the area of a rectangle? Yeah, it's length times width. Very simply, length times width. So your width is going to be delta x. And then the question is going to be, right, this is going to be why you have this delta x to begin with. Don't know what color, maybe purple, how's that? That width value is going to be delta x. So in general, this AI is L times delta x. And then the real question's now going to be right here. This is the real focus of the section. How do you find the length of that rectangle? The length, it's not too hard to do, but we're going to have different lengths. And you might say, what do you mean we have different lengths? Well, the length of your rectangle, like if I go back to this approximating rectangle here, right? The ith rectangle right in here. The length is going to either be one of two places here. You're going to use either what we call the left endpoint, And if you use the left endpoint to get that L, that's the length. So you have the length and you have your width, and we can find the area with length times width. Is that true? But what if you happen to use the right endpoint as the length? Obviously, it's not correct. Both of them are incorrect. So you can use, maybe I should use different colors here. I don't know. I'm going to say you could use, we'll use green and orange. We can use the left endpoint or the right endpoint for the length. And ladies and gentlemen, here's the problem. They're going to be both different lengths. Is that true? You say, what are you talking about? Well, if I use this length here in green, or if I use this length here in orange, those are different lengths. So that's based on what endpoint you use for your interval to get the length of that rectangle. And in one case, it'll be bigger than the other. And then you could do slightly better because you might say, okay, let's get rid of some, let's see if I can do something here with this, right? So the left endpoint in this picture, you get this rectangle. The right endpoint, we're going to get this rectangle. And then you might say to me, can you do a little bit better? And the answer is yes. We'll see 3 cases. The third case, which is a little bit better, is simply to use a value midway between the 2 endpoints. And if you use that value, the length would be somewhere here now. And you might get a better approximation, not just might, you will get a better approximation to that length. I know the colors are kind of, I hope you guys can see my point, but that's really the essence of this section here. When you look at the ith subinterval and you get the ith rectangle, you get the ith area, which one gives you the more, I should say, closer approximation? It's that midpoint area. But you got to look at the left endpoint, the right endpoint, the midpoint, and we can approximate the area. And that's really the essence of this section, ladies and gentlemen. And believe it or not, this has a lot to do with an antiderivative, although you can't see that at this point at all. Okay, so I just want to say to you guys, your work during the break on antiderivatives is not going to go without reward. Okay, anyway. All right, so you might say, how do you get the length? You guys know how you get the length? To just write this in general. Your length is f of the x value. Because on the curve, like if it's for the left endpoint, it'll be f of x I minus 1 in this formula. So if I said if you use the left endpoint, the length is f of x I minus 1. It's this endpoint down over here, what we're talking about. And remember, that length is the value of the function. It's really a y value, isn't it? Right in here, it's really your y value. That's why it's f of. And for the right endpoint, you say, what if I use the right endpoint? Well, here's what's going to happen. If you use the right endpoint of these intervals, the length is really going to be f of xi here. And the right endpoint is over here. Okay, and the highlighter right over here, down here in orange. So you might even say, well, all these colors are getting a little deceiving. Okay. The left endpoint of your interval and the what? Right endpoint of your interval is what we're saying here. This is your left endpoint, and this is your right endpoint of your interval, which is why I'm pointing those details out. And again, you might say, what's the best? The midpoint. So if you say, what if I use the midpoint to get the better approximation for area under the curve? Well, then that's really f of, you guys know how to get the midpoint? It's really the average of two numbers. And this is really that midpoint. So, was it purple? I don't know. So this is going to be what you replace your length with here. And that's what I'm saying right in here, right in the middle. I guess it was red. So red here. All right, so that really just covers what you use to get the what? The length. There's three different what? Options here for you guys. And then you might say, well, which option do I use? Well, it depends on what they tell you. Okay. Let me get the iPad back, ladies and gentlemen. I'll say we're here. I think this just has to reboot. Sorry. I'll go through some of the details that we're talking about here. All right, so let's see. Yep. Okay, we're back. Sorry about that. All right. We're back. So anyway, I just paraphrased everything. I got to the point. Now here's what we also, this is the graphic I use for all the right endpoint values. So as you guys can see, using all the right endpoint values of every one of those subintervals, x1, x2, xi minus 1, all the way, these are all the right endpoint values for every one of those intervals. And all the lengths are going to be f of those values. Okay. How do you get the area? Length times width. Okay. So this area in this picture, if you have n subintervals, you have n rectangles. So that whole area is approximately what? A1 plus A2 plus AN. So this accounts for all n of those what? Rectangles. All right, you guys okay with that? Easy peasy? This is calculus, by the way. It's crazy. All right. What about the right endpoint there, right? So, yeah, we started with the right endpoints, and that was orange. So let's use the right colors so people can see the consistency. The right endpoint values. Okay. Orange. All right. So here's the formula here, right? Your first subinterval right here, this is f of x1 delta x. The second rectangle, f of x2 delta x, all the way up to the nth rectangle, f of xn delta x. Or we get to use the what? This summation. Summation notation, where this is all the areas here. And this index goes from what? 1 to n. Here's your index. 1, 2, and it goes up to n. That's how you read that index for the summation. And then we define this as the right endpoint formula. That's Rn. So this formula is going to approximate the area under the curve. That's Rn, and n is the number of partitions. So if you take 10 partitions, n is 10. If you take 20 partitions, n is 20. if you take 100 partition, n is 100. So n is the number of partitions here, and that's called the right endpoint formula. All right, you guys okay with that? Anybody have any questions on that here? This is a way we can approximate the area. All right, well, right endpoint formula. You go, what about the left endpoint formula? Okay, we started talking about that. That's going to be all the left endpoints. You start at x0, you go to x1, x2. Okay, so these are all the left endpoints for every one of those intervals. So that your area is going to be, again, with the summation symbol here, same idea. Although you start here at 0 and you end at n minus 1, start at 0, 1, 2, and so on, up to n minus 1, your delta x is still here for each one because it's length times width. And so, ladies and gentlemen, you end up with what we call the left endpoint formula. And that's what you guys will use to approximate the area for the left endpoints. So it's going to depend on what endpoint you use. Either formula would be fine. Obviously, in this picture, the left endpoints will give you a smaller area. That's approximate. While the right endpoints will give you a what? Well, sorry, I had it backwards. The right endpoints give you the smaller area because you see some blank space. And then the right endpoints will give you a what in this picture? Oh, here we go. Left endpoints obviously larger in blue, right endpoints smaller. So they're approximations. So this is kind of this is the formula that I went through based on area is length times width. You factored out the delta x to this sum, right? It was factored out. So these are some formulas you guys can use to approximate area under a curve. So if you're writing a computer program that had to approximate the area under a curve, computers love this stuff. All right, you guys okay with that? And like I said, what's the best? The midpoint formula. And you say, why is that the best? Because you're getting the midpoints for every one of those bins. I'm sorry, those intervals, subintervals. And you can see now those rectangles are a lot better. Is that true? And so you have the midpoint formula, because all of these are midpoints of those subintervals, these m's, you got these delta x's, these are the areas, and factor out the delta x, so you get this what? This is known as the midpoint rule. And these are all midpoints for the length. So here's the pictures. That's how you get the formulas. Okay, these are the partitions. This is really calculus. All right, what do you guys think? Is that okay? The devil's in the details. This isn't so hard. Let's look at an example here. Okay? The function they gave you here is 1 over 1 plus x squared. And in this example, they want the area under the curve over the interval from -1 to 1. So let me draw. Do you guys want to close that door? Here's x is what? -1. Here, x is what? +1. So they want area under this curve here, okay? And we're going to go through this. So they want you to determine the following approximations over that interval. And you go, okay, well, how do I do this? Well, if they give you 5, you see this little subscript? What are they asking for? The left endpoint where n is 5. The right endpoint where n is 5. The midpoint where n is what? 5. So these are my n values, okay? So these are 5 partitions. So I'm going to start by saying n is 5 here. 5 partitions, okay? Now, here's what you guys want to do. Your interval AB, what's the interval? From -1 to 1. So when you start this off, draw your real number line here. And put where -1 would be here. You're really drawing this down here. Okay, you're drawing, let's undo that. You're really focusing on this portion right here, down here. From -1 to 1, the interval, but you want to have 5 partitions. So you might say, what does that look like? Well, let's draw some lines. 1, 2, 3, 4, what? 5. You guys okay with that? Here's 1. But you need to know what delta x is. You need the length of every what? Subinterval. So how do you get that length? Do you guys know how you get that length? This you use the formula. This is A, this is B. It's going to be the length of the interval, B minus A, over the number of partitions. So the length of every, I should say your delta x will be what? 1 minus -1 over 5. Or delta x will be 2/5. Delta x is going to be, do you guys know what 2/5 is numerically? Is that 0.4? I'm not awake. I haven't had coffee. I don't think that counts over there. 0.4. So you're going to have to now tell me here, what is each one of these values here? Using that delta x. Because n is going to be what number again? N is the number of partitions, 5. So -1 plus 0.4, you guys know what that is? It's negative point what? 6. And then what's plus another 0.4? Isn't that going to be, is that true? I think we're okay. What's this going to be? Is that 0.2? Negative 0.2? And then what? Add another 0.4. What's the next value going to be? Isn't that positive 0.2? Add another 0.4. What's that going to be? 0.6. And if you were to add another 0.4, does it make sense that that would be 1? Yep. So here's my point to you guys. You're looking at the 5 partitions here, where this would formally be known as x0, x1, x2, x3, x4, and x what? 5. So I'm going to put this delta x up here. Okay. It's already in your notes where that came from. And we're on our way. This, believe it or not, is the hardest part. Okay? You guys know what I'm saying? This is the hardest part. Now, what's your definition of Al5? Go back up here. Here we go. Look at the values you have for L5. Where do you start at? X naught. You guys know what that actually is? X naught is your A value in the interval. So you start at that A value. So L5, if you asked me, very simply is this. F of X naught delta X plus F of X1 delta X plus F of X2 delta X plus F of X3 delta X plus F of X4 delta X. These are all the left what? Endpoints. Okay, you guys okay with that? What I prefer though is this version. What is easier is to say factor out the delta X. So that is the easier version here. And what's the value here of each one? This would be -1. This would be what? -0.6, +0.2, +0.2, and then +0.6. What's your delta X again? What is that going to be? Point what? 4. But what is your function, ladies and gentlemen? What's the function here? That's your function. So you might even say to me, how do I actually go about this? How do you guys think you go about that? You got to plug in all those values. And I think I need some blank space. Does anybody know? Can I insert? Man, there should be a way to insert a page between these two. I don't think so. I need another. Here's what I'm going to do. I'm going to call this scratch. Nope. Okay, so here's your function. So ideally, here's what L5 would look like. 1 over 1 plus what? -1 squared. Because that's the function. 1 plus -0.6 squared. Oops, that's negative. I'm sorry, that's negative. One over 1 plus 0.2 squared, I think, and then 1 over 1 plus what? 1 squared. What's the delta X? 0.4. There it is. So these are all my what? Input values here. Okay, so this is a numerical approximation formula. Really, really simple to use. However, you might say, well, how do I get the value? Well, there's various ways you get the value. One way is to use what? Your calculator. So let's try it out. Okay? So, yeah. Yeah, I think there should be, 0.6, right? Yeah. Yeah, let me double check here. This would be 0.6. Yeah, I was looking back at that. And I'm like, wait a minute. And make sure this is going to be what? Here. There we go. So, yeah, looking back at this, you go, okay. What is going on here? Hold on. This should be what? 1. Wait. No.
It's correct. It's the last.
Hold on. Yeah, it'll be. Hold on. Negative 1.6. This will be negative 0.2. That's what's going on here. Okay. So this should be here. Let's correct this. Negative what? 0.2. And this would be positive what? 0.2. And this would be positive 0.6. So let's make sure the other page as well. Okay, so let's go back here. So let's make sure it's okay over here. Let's make sure this will be negative, positive. This one's okay. All right, so let's make sure. Looks like we're okay. All right, so back to the scratch and back to the calculator. So you say, well, what do I do with my calculator? Well, this is where the work's going to be. How well you guys know how to use your calculator, right? So I'm going to have to do a double parentheses, I believe, here. You might say, how do we do that? Is it a double parentheses or a triple parentheses? Well, I'm going to start with a double here. Let's see if we can do this. 1 divided by what? Parentheses 1 plus parentheses negative 1. Square that. Close this parentheses, okay? So you might say to me, what are you looking at if I do this here? Let's scroll in. I think that looks okay. So what am I looking at? You know what you're looking at? This first entry. Okay? Now you can look at the next entry. Let's do the next one. So you're going to have to say plus now. Parentheses here. 1 divided by, parentheses, 1 plus, parentheses, negative 0.6. Close that and square it, and then close that parentheses. That's your second entry. All right, so you say, what did I just enter? This is here. Let's now do the third. So in the TI, plus, parentheses, 1 divided by 1 plus, parentheses, what? Negative point what? 2. Close that and square it. Close that parentheses, plus, now we're going to do the next one. And you say, what's the next one? It's right here. So in the TI now, parentheses 1 divided by, close that, 1 plus 0.2 what? Squared, close that. There we go. Oops, yeah. Close it again, because that's a denominator position. Bless you. Bless you. Yeah. Let's double check here. Go back to the calculator. Yeah, I put it. That's correct, because those are negative numbers. So remember, how do we emphasize the numbers are negative? You put a parentheses. So the difference between this entry here, if I can scroll in, and the prior one is because that value was negative. So now that it's positive now, what I can do again is say plus now. Oh, I didn't want to do that. That's not the plus sign. Does anybody know how you undo? Is there an undo?
Yeah, you gotta go the up arrow.
The up arrow. And then go up again? All right. Uh-oh, I don't see. It's highlighted. I want to hit plus. That didn't do it. Oh, history. Yeah, you're right. There is a history. History. How about if I go down here? Can I hit delete? No. Oh, whatever. Okay. All right, we'll try that one again here. So trying to be careful here, not a good idea. Here we go. 1 divided by, close that. 1 plus, I have to put a parentheses, -1, close that and square it. Close this, there's your first entry. Plus 1 divided by 1 plus, now I'm going to enter a negative value again. Negative point what? 6. Close that, square it, close your parentheses, plus, well, I mean, I could do it that way, but we'll say 1 divided by, parentheses, it's another negative. 1 plus negative what? 0.2. Close that and square it. Close your parentheses. Plus a 1 divided by, now they're positive. So I put my parentheses. 1 plus 0.2. Square that. Close that parentheses. Plus the last one. 1 divided by 1 plus 0.6, square that, close that parentheses twice. So now this is everything that's in the what? These brackets here. Don't forget to multiply by 0.4, the delta x. So times 0.4. Now, ladies and gentlemen, what do we get? Let's go to the nearest thousandths. This is L5. This is the left endpoint approximation. What do you guys get here? Let's go to the thousandths here. As we go to thousandths, 1 point what? 557 to the thousandths? Is that right? And there you go. Here's your left endpoint approximation. Okay, well, now you say, what about the right endpoint approximation? right? You say, what about this again here? Do this again, but now do the right endpoints. Well, everything is the same here, sort of. For the right endpoint now, this is R5 now. So you might say, what changes now? Well, what changes is this. You start now for the right endpoints. You start where here? You start at x1, you go to x2, x3, x4, and x5. So if you went back to my definition here when I proved it, notice you started with what? With x1. So we're going to start with x1 here. You're going to start with all the right endpoints. Down here. So I'll write down the detail because I think it's helpful. x1, x2, x3, x4, and x5 now. Plug in what numbers? Negative 0.6 now. Negative 0.2. Positive 0.2. 0.6, and then a 1 here. Okay? So this will give you the right endpoint approximation now. Let's copy. And if we like, we can even copy this. And start to just enter those numbers. So here we go. Negative 0.6 squared now. And this, what's the next one? Negative 0.2 squared. And then positive 0.2 squared. And then 0.6 squared. And then a 1 squared. Okay? So this is now going to be, though, R5. And all these are the right endpoints. So you get to plug these values in. So it's going to be easy peasy lemon squeezy if we use our calculator, right? And let's try that out. You guys ready to try this out? This one is a little bit tough to enter in your calculator, but let's see if we get some, let's do it the same kind of way, right? So you say here's double parentheses, 1 divided by parentheses, 1 plus, you got to put a parentheses to emphasize that this is a negative number, so it's 0.6. Close it, square it, close your parentheses. That's the first entry. Again, now plus 1 divided by 1 plus, close it, negative 0.2 squared, close that, plus 1 divided by parentheses. Now this is going to be positive. 1 plus 0.2 squared. Don't need a parentheses for that one. Plus, because it's a positive number. 1 divided by parentheses. 1 plus should be 0.6 squared. Don't need a parentheses. The number's positive. Close that. Plus 1 divided by parentheses 1 plus 1 squared. Close that twice. Don't forget the factor of 0.4. Okay, so now you say, what do we end up with? Notice this. That's the same value. I think I know why, but it shouldn't be, but it is. You know why it's the same value? They're really the same numbers. You go, what? And you're squaring. That's the difference. So there's some symmetry with this curve. So, yeah, there's symmetry with the curve anyway. So it's the same value. Usually it's different. We'll see it in the next one. So R5, approximating the same value, place value. Also, it's actually the exact same number. And it's only because the function is what you guys see here and the symmetry of the interval. Okay, let's go back. The function here is what you see here. It's a symmetric function, and the values, even though they're different, it's a symmetric interval, but you're squaring, so the negatives become positives. So even if you said, hey, this one started with a -1 squared, you don't have a -1 squared. You had all these other values. That's right, but I have a +1 squared at the end here, and it's the same number. That's the deal. Anyway, so R5 will be the same. So we're answering that one. There we go. We have it. Now, the real work, though, if you said to me, how do we really do some work? It's going to be the midpoints. So I'm going to try to get rid of all these values. We're going to get some midpoint values now. So what's midway between -1 and a -0.6? You guys know? That's negative point what? I think it's -0.8. You say, how do I know that's -0.8? It's the average. -1 plus, well, -0.6, there it is, divide by 2, gives you, divide by 2, so we say -1 plus -0.6, then divide by 2 here. You get -0.8. So that's why I put -0.8. You guys know what's nice about delta x being 0.4? What's nice about delta x being 0.4? I don't have to get all the other midpoints. I could just add 0.4. Isn't that going to be, is that negative what? 0.4, add delta x, 0, positive 0.4, and then what? 0.8. You say why? Because isn't delta x, that distance, 0.4? So the distance between every one of these points is 0.4. So I can just simply do that, ladies and gentlemen. Use my delta x. And very often that's what I do personally. I just use the delta x value. So again, you say, well, what's going to be the midpoint formula here? M5. Well, put your parentheses, f of negative what? 0.8 plus f of negative 0.4 plus f of 0 plus f of positive 0.4 plus f of point what? 8, and I'll do it down here. Close that and multiply by that delta x 0.4. And I know color-wise, we did this in red. So we're finding midpoint values. That's your midpoint formula. So as you go through 5 partitions here, come on. I'm going to write it all again because I'm going to change the values. Okay. So you're going to have to enter all of these in again. But they're different values. Okay? Enter those in your calculator. Let's see what we get by the midpoint. So let's try it out. Okay. We'll clear this out. Double parentheses again. 1 divided by parentheses 1 plus parentheses negative 0.8. Close that and square it. Okay. Plus 1 divided by parentheses 1 plus parentheses negative 0.4. Square that. Close your parentheses. That's 0.4 now. Plus 1 divided by parentheses 1 plus, okay, I'll put 0 squared, close it, plus 1 divided by parentheses 1 plus 0.4, square that, plus 1 divided by parentheses 1 plus 0.8 squared, double close, times 0.4. And what did I do? That something doesn't seem right. Let's try that again. All right, let's try it again. Here we go. 1 plus negative 0.8. Close that and square it. All right, that's where it is. 1 divided by 1 plus. All right, close that again. Plus 1 divided by, close that. 1 plus, what comes after negative 0.4? Isn't that 0? All right, well, that's just 1, but okay. 0 squared, just for completeness. Plus 1 divided by 1 plus, now it's 0.4. Square that. Close it. All right. What comes after 0.4? 0.8 plus 1 divided by parentheses 1 plus 0.8 squared. Close that twice times 0.4. There we go. So M5 is going to be approximately again. And I didn't have all the other values. Okay. $1.57746. Anybody have the other values in your calculator? 1.5 what? I want to see go to a better decimal place. 577. I don't know, 577, whatever. So what you should get when you actually do all these approximations, they should be similar. And that's where all the work is, ladies and gentlemen. Now, you may not know this, but what's the function? This is coming our way. You guys don't know this. I actually know the exact value. So, what's inverse tangent? You guys know what inverse tangent on 1 is, by the way? I don't even think I need to do that. Isn't that pi over 2? In fact, here's what I'm going to do instead. You guys don't know this either. So pretend you're not seeing this. It's actually 2 inverse tangent 0 to 1. It's 2 inverse tangent 1 minus 2 inverse tangent of 0. And what's inverse tangent of 1? Does anybody know? Is that pi over 2? Anybody know? What's inverse tangent of 1? Let me think about this. Just got through my trig class. Is that pi over 4? I don't know. Inverse tangent is 0. Isn't that 0? So the answer is pi over 2. This is the exact answer. Yeah, I actually did the arithmetic in my head too quick. Anyway, what's pi over 2 anyway? Second, pi is somewhere over here. I can't see. Pi divided by 2. Is that pretty close approximation? $1.570. What have we been getting? 1.557. So all of what I just did here, this is calculus 2. It's not even calculus 1. But these are the antiderivative. You don't know what this is yet. The antiderivative of that function is inverse tangent, by the way. You don't learn that in this class. You learn it in the next one.
So this won't be in our test?
Yeah, it will. Not the integration part, but the what? The approximation part. In fact, I could do this stuff all day long. I can change this on you guys because, like you said, if I go to the next example here, on my notes that I did here, sine of x squared from 0 to pi, and that one's kind of a tough one. You say it's not. It's actually a lot easier. But you say 0 to pi. I should probably change that from 0 to like 1. Okay. So here's where 1 is. We can find the area under that curve from 0 to 1, and I'm going to change the partitions on you. Well, we can do 5 partitions, but delta x will be the same. You know, sometimes let's do like 10 partitions, right? So if n is 10, what's the hardest part of this, right? Your delta x, if you go from 1 to 0, this is the idea. Be 1 minus 0 over 10 now. Okay, change this. And that becomes 1/10. So when you do this partition again, you start where? What do you guys start at? We changed this question from 0 to 1 here. You start at 0. And then keep adding what? Isn't that 0.1, 1/10? This is 0.2. And then this is what? 0.3, 0.4, 0.5, 0.6, 0.7. Okay. 0.8. 0.9, and then what? 1. So the hardest part really is right here. The rest is using a formula, but you have to know what these values are, right? This is what? This first value is going to be, it's always going to be x0. And then the next one is what? x1, x2, x3, x4, x5, x6, x7, x8, x9, and this will be x10. It just has more partitions here. Because n now here is 10 partitions. So your function, though, is easier. You say, what do you mean it's easier? Here's your function. Sine of x squared. So in your calculator, you're going to use f of x being what? Sine of x squared. It'll be a lot easier to do. Make sure, though, it's set to what? Degrees or radians. What is this? Where's the students that took trig? Anybody? Anybody take trig? What does your calculator have to be set to? What are we talking about? Radians or degrees? These are radians, ladies and gentlemen. These aren't degrees. Radian measure. And, you can make this actual question this is actually a lot easier to do in your calculator. A lot easier than the last one. But can you actually integrate this one like I did the first one? The answer is probably maybe not. Whether it's calculus 1 or calculus 2. Because there's a lot more functions you can integrate than you can't. And you say, I don't even know what integration is. Well, come back tomorrow. Integration is going to be your antiderivative. So if you did your antiderivative homework, you really already know what this is. And that was the whole idea. Anybody do antiderivatives with their turkey, like I said? Hopefully. Anybody? Where are the people? Okay, good for you. Anybody not do it? Oh, uh-oh. All right. This antiderivative that I just talked about here, that I gave you guys in the first example, it's a calculus 2 antiderivative. It's not even a calculus 1 antiderivative. But it's kind of a classic kind of question that you're looking at with this function. It's a nice, beautiful, symmetric function that happens to have an antiderivative. Not every function has an antiderivative. This one may not have, sine squared may not have an antiderivative. You have to think about that one. Sine x does, but sine x squared might be a problem. So you're heading into an area where antiderivatives are going to be used. We'll see tomorrow. And, it's kind of a big deal. So hopefully you guys did your antiderivatives. Okay, I'll put a little bit of homework of approximation for you guys in Canvas, and we'll see you guys tomorrow. Take care.